give a talk about some very recent changes made to the Derived Foldable extension because I don't think they were very well advertised, and I just wanted to put it out there. It's nothing too crazy, just it can do more stuff than it previously could. So there's this wonderful trio of extensions in GHC, Drive, Functor, Foldable, and Traversable, and like their name suggests, you can just attach them to the end of a data declaration and they will automatically come up with a pretty reasonable implementation of all three of those. But there are some restrictions. They're kind of weird because there are type classes that take one type parameter, so it doesn't work very well for data types with existential constraints. If you try to make some silly little expression language like that and derive functor, foldable, or traversable, then it will come with an error saying that the last type parameter must be truly polymorphic. To get a better idea of what that means, we can take a look at what it's actually doing. So if you try to drive functor for that previous expression language I defined, I should have copied over the slide, but the important part is the return type of eInt is expression int, not expression a. So if you were trying to generate the code for a functor instance for expression, then it would come up with that, eInt of f of a. And the problem is that the return type needs to be eInt of b, but because it's constrained, it needs to know that it's actually eInt of int. And there's no way for it to come up with that because it has to be truly polymorphic. It has to be any type b. And there's no way you can produce that constraint, so it won't work. Foldable, however, is a bit different from functor and traversable in that the type parameter a only appears in argument type. It never appears in result type. So if you could hypothetically come up with the generated code for foldable, it would actually type check. And the reason that works is because the constraint for expression int in the int constructor gets consumed when you pattern match on it, but when you actually use it in the fold map implementation, then it kind of goes away because you mold it all together in a monoidal value. So it turns out you can actually do this, but currently GHC just won't let you because it's hard baked into the checks that it performs when you're trying to drive foldable or any of its cousins. So if you actually look at the full definition of expression and generate that code, it turns out it will type check. And if you're not familiar with the algorithm it does, basically it just goes through each of the arguments of each constructor and checks to see any occurrences of the type parameter. It will apply the function f to it. If there are any data types that mention the type parameter, then it will recursively call fold map, and then it accumulates all the values together using mapend. And here I'm kind of making up my own convention where if you have a constructor whose type is equal to the thing it's refined to in the JDT, then we also apply the function f to it. This is what I originally proposed for the design, but Simon pointed out that that's a bit shaky to do because it's not always clear when a type parameter is actually equal to the thing that you're refining it to, because constraints can appear in very surprising places. In that example below, they're pretty explicitly marked what the constraints are, but they could appear in some other constraint that doesn't actually mention int anywhere. There could be a superclass, and one of its constraints be that the type parameter is equal to int. So they can appear in very shocking ways. So it may not be a good idea to have it so that you fold over anything that's equal to type parameter. So the compromise that we came up with was, let's only do it whenever there is a type parameter that is syntactically equal to the type parameter as it appears in the data declaration. So in other words, if you had data GA, the only time you ever apply F is when it actually is A and not something which looks like A but isn't actually A. So that means the generated code for G, the only time you actually apply F is in the last example because there's an honest to God A and not something that's type parameter that's equal to it or something that's refined to int. And this change was accepted and it should be in the new version of GHC. Whatever that version number may be, I kind of lost track of what the naming conventions are recently. That's it. Well, I want a foldable instance. I don't know about other people. I just find it useful to be able to have some sort of generic way of breaking down an expression language into something easily without having to define an F algebra for it. Of course, that might be more general and useful in some cases, but this provides a relatively plug-and-play way of getting something quickly and easily. Yeah.
I find it just a little odd that I consider all of these types to be the same.
Well, yeah, it is kind of weird. The only reason we chose this design is just so it was very clear to the programmer when you would actually apply F to something. And because they're all more or less operationally the same, you can just, if you had int to g of int, you could rephrase it as A is equivalent to int, double arrow, A to g of A. And that way, when you derive foldable, it would give you the thing that you would expect. It's not the nicest looking thing in the world, but that's the way it is. That's one scenario I had in mind, is if you want to make a wrapper around a set and fold over that, then you could just put the OR A constraint in the constructor, and then it would be very easy to find a foldable instance instead of having to type it out yourself.